Hello, I'm George Worden. I'm working on improving the sort of long-term resilience of benzoxidine-based composite materials, generally for use in space, in particular low Earth orbit. So low Earth orbit, which is where the vast majority of spacecraft and satellites are located and will be for the foreseeable future, is quite a hostile environment for materials. There's a number of different hazards, in particular things like atomic oxygen from the upper atmosphere. There's micrometeoroids and debris that can physically damage it. And then there's various sorts of radiation, things like UV and cosmic rays. But as well as being very hostile, it's also very expensive to put anything there, because generally the cost of sending things into orbit can be sort of in the thousands of pounds or dollars per kilogram. So in order to keep those costs low, composite materials are potentially very useful because of their excellent specific properties. But unfortunately, the polymer component of the composite in particular is quite vulnerable to all of these hazards. So my PhD is working on improving their resilience to the environment. We are trying by introducing some silicon oxygen-containing nanoparticles called polyhedral oligomeric silsyl-groxane, which improves the polymer's resistance to atomic oxygen, as well as having quite a beneficial effect on mechanical properties as well. So first we talk about the atomic oxygen. I've exposed some carbon fibre reinforced polymer specimens using a plasma etching chamber to atomic oxygen fluences in sort of equivalent of 1 to 24 months in low Earth orbit. And as you can see, the addition of POS has a very beneficial effect. It reduces the amount of erosion from the oxygen by about 40%. And if you can see, I don't have a laser pointer, but the post-exposure CT scans of the materials, you can see that the polymer component in the top image has been eroded very preferentially over the fibre component, which is the fibres are the lighter part. And then in the second image, you can see there's a large resin pocket in the middle, which hasn't been eroded to anywhere near the same degree. And that's the panel containing POS. So you can see the very beneficial effect of addition of POS. So the oxygen resistance was the primary impetus for including POS, but it also has quite a beneficial effect on strength and stiffness and mechanical properties. So after producing some large composite laminate panels, about 0.5 metre in size, we've done a range of mechanical testing with sort of tensile, compressive, flexural and shear. And you can see the P1 is the 0% POS, P2 has 5% POS. You can see there's quite a big increase in the strength and stiffness of the composites. And also previous work in the literature shows that this benefit does start to drop off at higher concentrations. So only panels of 0 and 5% were made due to sort of time limitations, but above around 10%, those properties begin to drop off a bit. So this is really the ideal range for usefulness. And then, so current and future work, what I'm currently working on is adding some vitreomeric, attempting to add some vitreomeric additives into the polymer system, which will hopefully add a bit of self-healing functionality, which we tested by thermal cycling and possibly some ballistic testing, and then compression, either with and without sort of heating, which might be able to trigger the healing effects of the vitromers. Another big piece of work coming up is we're going to take some of the composite laminates to GSI, which is a heavy ion accelerator in Germany, which can create sort of galactic cosmic ray type equivalent radiation of heavy ions. And so there's two main goals for this. One is to determine how that will affect the properties, if it will degrade the laminates at all, and additionally to determine how effective this material is for shielding anything behind it from galactic cosmic rays. And finally, some of these, all of the data that I collect will be used for comparison against a small number of samples which are going to be sent to the ISS to be exposed to low Earth orbit, sort of in reality, as opposed to ground-based testing, which I'm doing. And then that comparison can be used to sort of validate ground-based testing methods. Thank you for listening. Are there any questions?